Hello guys, and welcome to Mrs. Schaaf's classroom. Today we're going to be studying more on thermochemistry, and in particular we're going to be looking at how to read a chart to find your delta H values, and then we're going to use those values to calculate the enthalpy of a system. Now in your textbook that you have, if you ever need to use it, your enthalpy chart is on page A5. It is chart B. And it says standard thermodynamic quantities for selected substances at 25 degrees Celsius. And it actually covers about, I don't know, 6, 7, 8 pages maybe. It looks like it goes all the way to, I'm going to show you a very short version of it, and but that is where you're going to get your values. So let's get started. So this chart that you see here is a very similar chart to what is in your textbook, except for the fact that it is very selected values that it has. So it doesn't have all the values that your textbook has. But if you'll look at it real quick, it talks about the species here, or the formulas if you would have. There's your delta H, your S, and your delta G for your Gibbs free energy. Your book looks the same way. It does have the same 3 columns. They are in different orders. Your S and your delta G are flipped, but other than that, they are in the same. So this is kind of what you're going to be able to see. Now, one of the things that I want to point out for you real quick here is that there are some things that have 0 delta H's. That would be like beryllium, boron, B2, calcium, carbon. So hopefully one of the things that you realize as I have read off of those, that each one of those that I read, carbon as a solid, there's 0. Up here, calcium, solid, 0. Bromine, gas, or bromine is a liquid, I guess, at room temperature, is 0. And beryllium is 0. So if it is an element in its natural state, okay, that's how we say it, an element in its natural state, it is going to have a delta H value of 0. So just be aware of that as you go through, but you should be able to find that also in your textbook. Let's get started on some problems. Okay, so before we get started on our first problem, we are going to record our formula to find the delta H of a reaction. It is the sum of the sigma, the sum of the delta H's for the products minus the sum of the delta H's for the reactants. So products minus reactants. So what you're going to end up with minus what you begin with. Products minus reactants. Okay, so as we begin the problem, the first thing that we're going to need to do is go through and find for us the delta H for each of the different, this is supposed to be, that didn't come off, that's supposed to be your arrow. So for each of your reactants and each of your products. And so we're going to come again to the table that we looked at and see what we can find. So be sure you know what you're looking for. Again, we're looking for pentane, oxygen, carbon dioxide, and water. Okay, so again, I'm just going to use the table of values that I was showing you earlier. And so if you will, again, scroll down through, we're going to first hit carbon. And again, we were looking for C3H8. So scroll until you find, so here it is. So my heat of fusion values is a negative 103.8, and again, kilojoules per mole. Okay, our next one that we need is carbon dioxide. Down there's carbon dioxide gas, and it is a negative 393.509. And then our next one was, let's see if we can find hydrogen or water. And so water, now you do need to know which one you have here. And I believe in our equation it was as a gas. And so we've got a negative 241 0.818. So do double check that to make sure it's a solid, liquid, or a gas on that. And then our final one is oxygen. So let's just keep strolling. Oxygen gas again, and that is again the difference between oxygen, ozone, and then oxygen without. So it is 0. So let's go back to our problem. So let's go ahead and again look at our formula. I went ahead and noted it there for us so that we would have it easily. And so our formula again is the sum of the delta H's for our products minus the sum of the delta H's for our reactants. Okay, as we go to calculate this, we're going to do the sum again of the delta H's of our products. Now, one thing you have to be careful with is there are coefficients. So I have 3 carbon dioxide. So when I come to do my products, it is the sum of 3 carbon dioxides, and carbon dioxide was 393.509, plus I have 4 waters. Each water is a negative 241.818. Now again, remember our formulas for our labels for our delta H is kilojoules per mole. So when I look at all of this, this label is again kilojoules per mole. So it's the sum of my products minus the sum of my reactants. And so when I do my reactants, I have 1 propane, which was a negative 103.8, again, kilojoules per mole. Put that down here just so it makes it a little bit easier. Plus, I have 5 oxygens, but oxygen is just 0. Now, don't skip that and leave that step out. You do need to show it so that we know that you know enthalpy is for oxygen. Okay, so the rest of it is now just computation. So let's go through that. Okay, so I have run my first set of numbers 3 times the negative 393.509. I've got a negative 1,180.527 kilojoules per mole, plus the 4 times the negative 241.818 is a negative 967. So again, double check my values there and make sure that is correct. On this side, our sum of those, we just had 1. And so we could actually kind of remove the summation symbol if you wanted on there. Take that part out because we really don't need summation anymore because we only have the 1 value. Now be careful, this is a minus here, and we have our sum to also be a minus value or a negative value on that. So kilojoules per mole. Okay, let's continue on with our next set of calculations. And so we need to just come in here and add these 2 together. Okay, so I put the 2 together. I've got a negative 2,147.799. Again, double negatives here is actually going to make that a plus 103.8. Again, my label for everything is a kilojoule per mole on that. And then let's put those 2 numbers together and see what we get. And so I get a total as my delta H answer as being a negative 2,043.9 battery dyne or something. Again, kilojoules per mole. We're going to do significant digits again on that for the most part, and most of our values were out 6 on that, so it looks like we're pretty good with our final answer. Now, I would say I would have to look at the standard practice on that as to whether or not, because I know on our worksheet it went all the time to whole numbers, so I'm assuming for the most part that's going to be a standard practice. If that is the case, we're at a negative 2,044 kilojoules per mole as a final answer for the overall of this equation. Now, the next thing we need to decide is it an endothermic or an exothermic? So if you go back to your delta H values, delta H means that it was losing energy, so losing energy to the surroundings. Therefore, this should be an exothermic reaction. Exothermic reaction. Okay, so we're going to do another problem real quick. And again, you need to go to your table if you have it in front of you and look up the values for hydrogen gas, chlorine gas, and hydrochloric acid. Okay, I hope you paused yours to see if you could find it yourself. But as we discussed earlier, chlorine gas in its natural state is a diatomic, so it does have delta H of 0. And then hydrogen, same way, it's a diatomic, 0. And then your next one is your hydrochloric, and your hydrochloric is found underneath chlorine. In this case, you'll have to check to see how your book lists it. Again, make sure you know whether or not you are doing hydrochloric gas, or so hopefully you noted that our hydrochloric was in the gas. So we're going to be using the negative 92.307. Okay, let's go back to our problem. Okay, so we're back to our problem. So let's get our formula down. We know that our delta H of our reaction is, again, the sum of our products. So the delta H of products minus the sum of the delta H's of our reactants. Okay, so we'll go ahead and fill those in. So the sum of our products, well, in this case, we only have the one product, so we really are not doing a summation, but we have two of those, and each one being negative 92.307 kilojoules per mole. So we'll go ahead and write it that way. And then the summation of our reactants, and in this case, we have one hydrogen gas and one chlorine gas. And so we have 1 times 0 plus, again, just 1 times 0. Again, label is kilojoules per mole. And I know that seems a little bit redundant to write that down, but that again shows me that you know each one is 0. So we're going to go ahead and do our calculation. So we just need to take the 2 times the negative 92. So our value that we're going to get here is a negative 184.614. And again, kilojoules per mole. And of course, we're minusing 0 on that. So we know that this is our final answer. So in this case, our delta H of a reaction is a negative 184, with our same story as we had last time. Since it is negative, it is giving off, so it is exothermic. Now, one of the cases where you're going to see that it's endothermic, if this reaction had in fact been a decomposition of hydrochloric acid into your hydrogen and chlorine, and so these would have been flipped around, and you would have had a minus, and then therefore it would have been a positive on that. So hopefully you realize that that one then would have been endothermic. So there's our final answer. Another example. So again, you'll be working some of these. Good luck. And again, if you have any questions, please let me know. And again, Mrs. Schaefer's classroom is signing off.